Okay, hello and welcome to my YouTube channel again. My name is Nathaniel. So in today's code overview, I'll take you through gas in the Ethereum virtual machine. Gas in the Ethereum virtual machine. So in our last video, I showed you how the EVM handles stack related opcodes, but I was unable to take you through all the opcodes related to stack. But maybe in my next video I'll show you all of that. But in today's video, what I want to show you is how gas are managed in the EVM. How gases are managed in the EVM. How gases are managed in the EVM. So the first thing I did here is, this is actually an enum containing all the opcodes related to stack. And what I did is, for each of these opcodes, there are amount of gas assigned to each of these opcodes by default. And this is not just something I give out, it's something I got from the spec. Yes, from the Ethereum virtual machine spec. So when there is a byte code that executes the push one in the EVM, the gas that burns for this execution, for such execution rather, is 3. And for add is 3 2, for pop is 2, for stop is 0 because there's literally nothing happening, just to stop it an execution. For equality is 3. So this is it here. Now these are all the opcodes that are related to stack, all the opcodes related to stack. So we are going to see how these things correlate with gas in the EVM. So after defining the amount of gas each of these opcodes burns when they are executing by default, is we now implement them here. So remember this instruction here. This instruction here calls this decode bytecode function, which is in my opcode.rs file. This is my opcode.rs file that takes in my bytecodes. So it runs the bytecodes and compares them with my opcodes. These are, for instance, this is what this function takes. It takes in these kinds of bytecodes. It checks the inputs we're taking here. Does it correlate? So it takes 0x60 and then it pushes it 0x50 and it calls the pop function. It calls the pop. This pop opcode is executed 0x80 to 0xf0 this thing here. Okay, so this line 0x80 to 0x85 calls the dupe opcode, and then the 0x9 and the 0x9f calls the swap. So this basically is what this decode bytecode does. It takes in the bytecodes and it assigns them to their respective opcodes. So remember, we've assigned amount of gas that each of these opcodes is permitted to burn for a transaction, right? So when this pool opcode is executing, how many amount of gas are we expecting to burn for the pool? Is 2. Exactly. So this is what our instruction does. It takes them here, and the first thing we did is we set a condition. And not just showing you how gases work, I'm going to show you program counter. It tells the EVM where exactly the operation is happening. So by default my program counter is 0 here. So what I did here is, this instruction length here returns the amount of bytecodes that my EVM is reading at the moment. So what we're saying is, it is not expected that the instruction, let's say for instance the instruction my EVM is reading in the bytecode is 15 bytes. Maybe the number of bytes that my EVM is reading at the moment is 15. I'm not expected to have a program counter counting more than that. Yes. And the next thing condition I said there is for my gas. So my gas must not be equals to 0. If my gas is equals to 0, meaning I'm out of gas, this guy is going to print out of gas, halting execution. But if all of these conditions are checked out, have passed, this is actually going to work. I'm going to call the execution code. This is where the engine exactly. This is literally the engine function. The execute opcodes will start to work. This is going to call the execute function opcode. The execute opcode function rather. Yeah. So the first thing this function does is it checks the number of gas that a particular opcode burns for a transaction. So this function actually takes an opcode, but what we're doing is that we are reading the opcode for this transaction, opcode for this particular transaction. So in my opcode function, in my opcode file, I have this gas cost that I define the amount of gas by default, right? So it checks, okay, what's the amount of gas that this opcode is burning at the moment, and then it saves it as gas cost. So the next thing I did here is I set a condition that checks the amount of gas I have at the moment. Is it less than the amount of gas that I'm willing to burn for this transaction? So if the transaction fails, this is printing out of gas execution halts. Out of gas execution halts. Yeah, and then the next thing I did here is for self here, I updated the amount of gas I have by subtracting the amount of gas that this opcode burns. Then I update my current gas. So all of these things I'm going to show you. I'm going to show you all of this. So let me run my code and show you this. Cargo run. So right now, this is the amount of gas we have. This is the amount of gas we are willing to burn, 20. This is gas that I've set 20. So now the bytecode I'm using to test this gas here, this is the bytecode. These are the dummy bytecode I'm using to test my transactions to check the amount of gas burning. So this first opcode here is a push. This guy too is a push. This guy too is a push. This is for dupe. So these are opcodes with different opcode related abilities. Yeah. So my EVM takes this guy and runs them through this guy here. It checks, okay, these opcodes that we are taking, what opcode is related to these bytecodes, and it assigns them. After assigning all of these guys here, then my EVM works with them. My EVM works with them by checking their gas fee, by checking the amount of gas we're willing to burn at the moment, checking the amount of gas we're willing to burn at the moment, and then it executes. So at the moment here, the first thing we did is, remember, we have total amount of gas is 20, right? So the first transaction burns 2 gas. It's a POP, so push 1 is executed, and from what we defined here, for a transaction that involves push, the amount of gas that burns is 3. So when we burn 3 out of 20, we have 17 gas left. The next push burns another 3, we have 14 left. The next push burns 3, we have 11 yet. And the bytecode now executes the dope2 opcodes, and the dope2 opcode burns 3 gas, and then subtracting this, we have 8 gas remaining, and the next bytecode calls the add opcodes, and the remaining gas we have for the add opcode is 3 gas, so 8 minus 3, we have 5. And then for POP here, we have 2, so 5 minus 2, we have 3 gas remaining. And now we want to so I guess execution stops, remaining gas is 3 at a PC. So the number of instructions that our EVM is reading at the moment is 6. Don't worry, I will create a separate video that will explain the pointer counter for you, but for now my emphasis is just so that you understand how gases work within the EVM. But now let me make this transaction fail by reducing the amount of gas I have. So in this function, in this code, the amount of gas I have is 20. What if the amount of gas is 10? We now know that from here, I guess from here the code should fail, or rather from here the code should fail. So let's test this and see. Let's test the code and see. Awesome. So push takes in 3, we have 7 gas left, minus 3 we have 4 gas left, minus 3 we have 1 gas left. Now we want to duplicate, it's unable to duplicate, and then out of gas, execution halt, execution finished, remaining gas is 1. So are you seeing how this works? So you're not just seeing how, you're not just knowing that when smart contract are executed, gases are born. You know what it means when they say gases are born, because you're seeing the code. You are seeing the code. You are seeing the code. But if I update the amount of gas I have now to be 15, I guess this should pass. I guess this should pass. Okay, out of gas, so we have some other bytecodes to implement. Exactly. So what our EVM does is that it works with the gas. It works with the gas. Yep, and this has passed. So execution stop, remaining gas is 8. Execution finish, remaining gas is 8. So this is all for now regarding gases. So in the next video I'll try to take you through program counter, so that you see how when each transaction is happening, how the EVM knows where you are, which transaction to implement at the moment. Yes, so all of that, we'll see that in the next video. So see you soon. Bye.